In this video, I am going to discuss gas chromatography. So in the previous video, we talked about gas-solid chromatography. So this is a gas-liquid chromatography. So the partitioning process for the compounds to be separated are carried out between moving gas phase and a stationary liquid phase. The temperature of the gas system can be controlled because the column is contained in an insulated oven. The concentration of any given compound in the gas phase is a function of its vapor pressure. And if you want to know more about this, then this is a really great resource. So these Chem Libre text things can be kind of hit or miss as far as being good resources, but I found this one to be an excellent resource on gas chromatography if this is something that you are more interested in. And so in general, what we're doing here is we have our gas flowing through this column. We inject our sample into it, and it will move through this column, which is often spiraled like this so that we can get a longer column length. And then the compounds will come off of the column at different times based on how they interact with the stationary phase. And so we can again get peaks from that. And so the columns for this look like this. So like I said, they're often spiraled like this. They're very thin. They're capillary columns. And so they have the stationary phase. Often they are adsorbed to the outer sides of the tube here. And then there is an open tube in the middle for which the sample will move through within a carrier gas that I will discuss here in a little bit. And so you can get packed columns, but most often they are going to be coated on the sides of the column. And so these are some different kinds of stationary phase we can get. So we can get the stationary phase in what's called this WCOT, or this SCOT, or this PLOT, which I will discuss in more detail later. So they're just different ways of having your stationary phase adhered to the sides of the column. So like I said, these are very thin columns. So we can see here this has internal diameters, and so these are in micrometers. So this diameter is in the micrometer range. The reason we want that is because we want the gas in the internal part of this to be in as much contact with the thin layer of the liquid, the stationary phase, as possible, because we want it to equilibrate with the stationary phase. And so, like I said, these are the different kinds we can have here. So in all of these, we have it adhering to the sides of our column here. And so the PLOT contains immobilized porous polymer and alumina. And so this is actually going to be solid stationary phase on this, where the ones like this or the WCOT have a liquid stationary phase on the sides. And so this is just looking at the efficiency for different diameters of our column here. And so this one right here, the 0.25, is going to be often the most common one here. And so again, it's a trade-off between having high efficiency, which we get if we make these thinner, but then we lose the capacity to carry each analyte. And so oftentimes we go for this middle one right here to get that trade-off between the highest efficiency and the best capacity for the analyte. So like I said, the efficiencies of the internal diameter and efficiency and sample size are represented in this table here. And so here we can look at what's called the phase ratio. So it's just the ratio of the internal diameter to the film thickness. And so that's something else we want to take into consideration here. And so it's just calculated like this. And so we usually want, for general purposes, we do the 100 to 400 ratio of the column radius to the film thickness. So then when it comes to the length of the column, we again want to look for good efficiency here, but we also want to have good resolution. And so it's another trade-off between having that efficiency and the resolution for this, just like it was with the column chromatography. So like I said, these are the different kinds of wall-coated. There are packed versions of this, but those are a lot less common. So we can have the wall-coated open tubular, the porous layer open tubular, which is just a solid in here, and then the support coated open tubular, which has these solid beads inside that we then coat with our liquid stationary phase. If we go down here, these are the types of stationary phase that are quite common, especially this silicone oil and the polyethylene glycol. Those are probably the most common kinds that you will see used in gas chromatography. And so there are multiple different kinds of silicone oil. I actually only listed a few of the types of R chains that you can have here. There are other different R chains that you can have that can make it more polar than this. And so, like I said, the silicone oil is a very common one because it has a lot of versatility. And so that is probably going to be the two kinds that you see most often. All right, then the carrier gases, which are the gases that will push our product through the internal ring of the column. Helium is one of the more common carrier gases because it is compatible with most detectors. For flame ionization detector, and I'll discuss the detectors very briefly here in a little bit. The N2 gives a lower detection limit than the helium, and so that means that we can see things that are a lot less concentrated than we could with the helium. So optimal flow rate increases with this, so we oftentimes use hydrogen that has optimal flow rate. The fastest separation can be achieved with the H2 gas, but it can catalytically react with unsaturated compounds, and so it's not always the best one to use, and it's also not good if we use mass spec with it because it can break down the vacuum pump. So hydrogen and helium give better resolution than N2 at high flow rate because these solutes diffuse more rapidly through the H2 and HE than they do to the N2, and most analyses are run at carrier velocities of about 1.5 to 2 times as great as the optimum velocity because this gives us a better unit time here. So a small decrease in the resolution is tolerated in return for faster analyses. Because we don't have infinite time to run these analyses, you do want to get them out quicker, and so a small hit to the efficiency is going to be acceptable if we can get more analyses in. All right, so the principles of separation here. So the carrier gas is allowed to flow through the column supporting the liquid phase. The mixture of compounds, so our sample here, are introduced into the carrier gas stream. The components are equilibrated between the moving gas phase and the stationary liquid phase. The separation is based on which compound interacts most strongly with the stationary phase. The stationary phase is adsorbed onto the surfaces of the support material. This right here, this is all taken from that great resource that I discussed at the beginning, so this is all just copy pasted from that in this part right here. So elution order in gas liquid chromatography depends on two factors: the boiling point of the solutes and the interaction between these solutes and the stationary phase. A mixture's components have significantly different boiling points, then the choice of stationary phase is less critical. If two solutes have similar boiling points, then a separation is possible only if the stationary phase selectively interacts with one of the solutes. So only if it interacts with one of the solutes more than it does with the other. To increase the interaction between the solutes in the stationary phase, the temperature is usually set slightly below the lowest boiling solute. So we don't want this to have one of these solutes always in the gas phase. We want it to equilibrate between being in the liquid and the gas phase for this. As a general rule, nonpolar solutes are separated more easily when using a nonpolar stationary phase and polar solutes with a polar stationary phase. So there are several important criteria for choosing a stationary phase. It must not react with the solutes, so you don't want a stationary phase that's going to react with your solutes, and then those solutes ruin your column and they don't actually move through the column. So it must be thermally stable, so we don't want our liquid stationary phase to actually evaporate and itself move through the column. It must have a low volatility, which is kind of the same thing here. So I think thermally stable is talking about we don't want it to react as it gets heated up. And so the low volatility has more to do with the actual evaporating of our stationary phase. And it must have a polarity that is appropriate for the sample's components. There are three things that affect the solubility of a gas in a liquid. So chemical reactivity between the liquid and gas, the pressure, and the temperature are important factors. The more reactive a molecule is toward the solvent, the more likely they will dissolve within it. So for instance, carbon dioxide is very soluble in water because it can undergo this reaction here, which if you've taken an anatomy and physiology class, you'll know that this is the reaction that we use to buffer our blood. But the CO2 can react with water and form this, which can then go on to deprotonate. And so that makes CO2 quite soluble in water, which, if you know anything about climate change, you know that the oceans are sucking up a lot of the CO2 from the atmosphere, which acidifies them using this mechanism right here. But anyway, by increasing the pressure, we usually increase the solubility of some gas G in the liquid. This is known as Henry's law. And so we have this constant of proportionality here. So our concentration of the gas is going to be equal to that proportion times the vapor pressure of the gas. So decreasing the temperature increases the solubility. So this is different than when we're dissolving solids in a liquid. So here, instead of increasing the solubility when we increase the temperature, we actually decrease the solubility when we increase the temperature. And this is because when we increase the temperature, the molecules have greater kinetic energy if we increase the temperature, so they have lower kinetic energy if we decrease the temperature. And so the molecules have lower vapor pressure, which prevents them from escaping the liquid. So here are just some actual data for the solubility of different gases in a liquid as a function of the temperature here. And so we see that those actually go down as we increase the temperature. All right, so what we are doing inside the column, so this is sort of a look inside the column where the liquid here is our stationary phase. This is what it's adhered to, and we have heat coming in from the oven outside of this. And so we want to equilibrate our compounds here with the liquid. So if they are less volatile or more soluble in the liquid, then they will be favored going into the liquid and interacting with the liquid. If they're more volatile and or less soluble, then they are going to come out of the liquid and stay in the moving gas stream. And so they are going to move faster through the gas stream here, so through our column. And so what we have happen, we put our sample in here. It has multiple different things. Some of these will move fast through the column, some more intermediate, and others will move more slowly. The things that are interacting with the liquid stationary phase are going to move more slowly through it. And so the things that move faster through it will come off faster, and so then we will get the peaks for those faster. So compounds with low boiling points will generally travel through the column faster than compounds with higher boiling points. And one of the reasons for this is that liquids tend to be more soluble in other liquids than gases are. So the carrier gas must not move so rapidly that molecules in the sample in the vapor phase cannot equilibrate with those dissolved in the liquid phase. So if the flow rate is too slow, though, the bands broaden and that can reduce resolution. So again, we want that trade-off of moving fast enough but not too fast. And the molecular weights, the functional groups and polarities of the component molecules of your mixture to be separated must be considered when a liquid phase is being chosen. So a different type of material is generally chosen for hydrocarbons, for instance, as compared to esters. And the materials to be separated should be able to dissolve in the liquid. Compounds that resemble one another closely in general will require longer columns because we need to get more separation on those if they look too much like each other. All right, so just a couple of the common detectors here. These aren't all the detectors that you'll find, but these ones are quite common, are the thermal conductivity detector and the flame ionization detector, where the thermal conductivity detector uses a wire heated by a constant voltage and measures how fast heat is conducted away. When it is just the carrier gas, it remains constant, but with the vapor stream changes composition, then that will change. And so this is measured against a reference flow of carrier gas. So it looks something like this, where we have our reference flow here and our column flow, and so we can measure the difference in which these conduct the heat away from the gas here, and that will tell you whether something is coming off of the column that's not just the carrier gas. So the FID here, the flame ionization detector, we have the effluent goes into the flame produced by combustion of hydrogen. The burning of the organic compounds produces ions, and the resulting electrical signal is recorded. So we have our sample coming up here through the column. It mixes with this H2 right here. It then burns in this flame. The ions come up off of here. They collect on these collectors, and that changes the electrical signal going through them. And so this is more sensitive, and so you can use smaller samples. It does not respond to water, and so can be used for aqueous solutions, but it is more difficult to operate, and detection process destroys the sample. So these are a few of the other detector types here. So I only talked about the flame ionization and the thermal conductivity. If you want to know more about these, you can look these up online. So we have like the barrier discharge ionization detector and the electron capture detector and so on and so forth. And so again, these have detection limits and the detectable compounds. So you have to be able to choose the one that you want based on your needs. So retention time, so for a given set of constant conditions, things like flow rate of carrier gas, column temperature, column length, liquid phase, injected port temperature, the retention time for any compound is always constant. So retention time is measured from the time of injection to the time of maximum detector signal for the component being observed. When obtained under controlled conditions, the identity of the compound can be determined. But to do this, you'll want to calibrate by running a pure sample of a known compound along with your suspected components, or at a different time than the suspected components, but under the same conditions in order to compare them. And so again, we get our retention times here. So this would be the retention time T1, T2, T3, and this right here would be when you actually put it onto the gas chromatography column. And so we can do quantitative analysis here, which is going to be similar to what we saw in the column chromatography. So we look for the area under a gas chromatograph peak because that is proportional to the amount of compound eluted. And so the molar percentage composition of a mixture can be approximated by comparing relative peak areas. This is often done by triangulation, and so we just multiply the height of the peak by the width at halfway up the peak there. And this only works well if the peak is symmetrical. And so similar to in the previous video, so if we want to find the area of peak B and peak A, where this is our peak B here and our peak A here, we get the area under it by just multiplying the height by the width at the half height there for each of these, and then we just take that number and divide it by the total amount there, and that gets us our molar percentages here, just like we saw with the column chromatography. So one other thing I wanted to mention, because this is quite common in organic and biochemistry labs, is gas chromatography mass spectrometry. And so this is the gas chromatograph is coupled to a mass spectrometer. So in effect, the mass spectrometer acts as the detector here. So the gas stream emerging from the gas chromatograph is admitted through a valve into a tube where it passes over the sample inlet system of the mass spectrometer. So essentially it just goes right from the GC into the mass spec so that we can get the mass spectrum of our compounds that are coming off at different times. So we are separating the compounds and then getting the mass spec for each of them, which allows you to better tell what is actually in each of the peaks coming off of your gas chromatogram. So molecules in the gas stream are converted into ions in the ionization chamber, and thus the gas chromatogram is usually a plot of timer versus ion current, so that's a measure of the number of ions produced. At the same time, the ions are also accelerated and passed through the mass analyzer of the instrument. The instrument therefore determines the mass spectrum of each fraction eluting from the gas chromatography column. So like I said, this is a very common instrument used in organic chemistry labs. And so your school, if you're taking this as like a sophomore level organic chemistry class, might actually have a GC mass spec in their laboratory. And so this is something that you might use. And if you're reading papers in organic chemistry, you might often see data given by GCMS. But anyway, that was everything I wanted to talk about in this video. I hope you found that helpful, and I will see you in the next one.